So in 5.5, we talked about random variables, what exactly they were, okay? And basically, it's all the values a variable can take on in a certain situation, and then their corresponding probabilities. And we basically talked about discrete, ones that you can count, random variables that you can count. We haven't looked at continuous really, where ones that you can measure, like where there's fractions and stuff. So, like I said, if the situation is you flip a coin 3 times, you know, what's the what's the distribution of getting heads when you flip 3 times? Well, the variable can take on 4 values: no heads, 1 head, 2 heads, or all 3 heads. Okay, so in that situation, the random variable can take on 4 values. If you roll a die 4 times, okay, and you want to count the number of times an odd number happens, okay, well, it could happen once, it could happen twice, it could happen 3 times, it could happen all 4 times, or it could not happen at all. So there's 5 values the random variable can take on. And then we talked about how to find the mean of a distribution of random variables, okay? And because we talked about the mean, now we're going to talk about the standard deviation and also the variance. Just revisit that. So this is a situation that we looked at in the last lesson where we had a game of roulette. X equals the number of winnings from a $100 bet on black. So in this situation, the variable can take on only 2 values. You either win 100 or you lose 100. That's it. There's no other values the variable can take on. And the probability of winning 100 was 18 black out of 37. And the probability of losing 100 was 18 red and green, so 19 out of 37. And we calculated the expected value, or the mean, to be negative $2.80. And what did that mean? That means that if we play this game many, many, many times, on average, each time we're going to lose $2.80. Okay? So if we can find the mean of a distribution, we can also find the standard deviation. So the standard deviation of a random variable, and discrete, because that's what we're talking about, measures how much the values of the variable, what's that phrase we use for standard deviation? Typical distance, or typically vary from the mean. So remember, to find standard deviation, we had to know the mean. Because what we did is we took each value in the distribution, subtracted the mean, squared them, added them all together, and found the average. Okay? Before we find the standard deviation, we find the variance of X. The variance is simply the standard deviation squared. I gave you guys this when we first talked about the variance is the standard deviation squared. This was way back from unit 1. Or the standard deviation is the square root of the variance. Okay. So if you got the variance, you go to standard deviation by square rooting. If you've got the standard deviation, you go to variance by square. So we use the following formula. So what we do is we take each, so defined, and remember, Standard deviation is that symbol of the random variable, or sorry, that's variance, pardon me. We're finding the variance first. So that's why I put a square, because this is standard deviation. But if it's got a square, that represents variance. So what we do is we take every value the random variable can take on. We subtract its mean, square it, but then just like when we found the expected value, we took each value and multiplied by its probability. So you take each difference and multiply by its corresponding probability. And then you add all those together. This will be a formula you'll get. You'll always get this formula. Okay. Actually, more specifically, you'll get this formula. You won't get the variance formula, you get the square root. So how do you find the standard deviation? Well, you do that whole variance thing. And take the square root of it. Okay. And many times, instead of this symbol, you'll see this. Sorry, this is bar x. This is bar x. Okay, so let's find the standard deviation of the roulette game. So we want to find the variance first. So what we have to do, or bar x, we have to take each random variable it can take on. So the first one is you won 100, it was 100, minus the mean, which we already found in the, sorry, minus the mean, which we already found in the last lesson. And remember, the mean was negative 2.8, so that actually changes to a plus. Okay. Square it times by its probability of getting winning $100, which was 0.486. And then we have to do that for each value the random variable takes on. Well, there's only one more. The random variable could be negative 100 minus its mean. So minus negative 2.8 squared times the probability of getting losing $100 or winning negative $100, which we found in the table was 0.514. I add all these things together. That's the sum. And that'll get me the variance. So I've got to do what? 100 plus this squared times this. Negative 100 plus this squared times this. And when I do all that calculation, I will get 9,992.16. That's the variance, remember. To take it one step further, to find the actual standard deviation of the random variable, just take the square root of that number we just found. And you get approximately 99.96. And remember, there's units here. So what this means Okay. The winnings typically vary from the mean of negative $2.80 by about $99.96. Okay. And that kind of makes sense if you think about it, because if you play several times, the mean is negative $2.80, but that's pretty close to zero. Okay, which means that every time you play, it's going to vary by 99.96 or about $100, which makes sense because you win $100 or you lose $100. And over time, it averages out to about zero, but it's negative $2.80. Okay? But that's how we would interpret the standard deviation. Okay. All right. One more thing on standard deviation and variance. So imagine this game that involves a random variable that takes on two values. Okay. So a casino comes up with this game for high rollers. You roll a six-sided die. If you roll 5 to 6, you win $1 million. But if you roll 1 to 4, you have to pay 300,000. Okay. Well, and you're told the expected value. Remember, this is the same as EX. And then this is the variance. Or sorry, this is the standard deviation. It's the square root of the variance. So if you could play this game only once, would you play? I mean, $1 million. What's the chance of winning $1 million? 2 out of 6. 0.667. Probability of losing. Sorry. 0.333. And 4/6 is about 0.667. Okay. So what does this mean? This means that if you play many, many times, on average, you'd win over $100,000 if you played many, many times. Obviously, you need the money to play. Okay? Because there's a good chance you may lose. You have to cough up 300,000. However, if you look at the standard deviation, that's huge. It varies wildly. Okay? So is this a game that you would really want to play, right? Even though this looks good, this doesn't. Okay? But again, even to get in this game in the first place, you would think you got to have a few million on hand, because you may lose the first few and you're going to have to pay before you start winning. But eventually, over the long run, you will win. Okay? So basically, it's probably not. Because even though the expected value is high, standard deviation is really high. So that means you could go from winning a lot to losing a lot. That's what that means. So yeah, you've got millions to burn. Maybe it's a game you want to play. Okay? Because if you played it a whole bunch of times, probability says that you should come out with more money in the end. Okay? But if you don't play it many times, it's a high rollers game. Okay. So that's what random variables, how we find the mean or expected value, how we find the variance, and then the standard deviation. Way back in, I think this was unit 2, we talked about what happens if you add a constant to a distribution. What happens to the mean? What happens to the standard deviation? Do you remember that? Like if you had a distribution, some distribution, and the mean was 70, and you added 5 to each number in the distribution, what would the new mean be? It would be what?
It would be the same thing.
No, it wouldn't be. It would be 75. It goes up by 5, right? If you took away 5, the mean would go down to 65. However, the standard deviation, okay, that doesn't change if you add or subtract, but it does change if you multiply or divide. Okay, that's basically from unit 2. So really, this is just a repeat, except we're using a probability distribution. So we can go through this fairly quickly. So adding and subtracting. So let's say you play this game. Remember, it was you won $100 if you bet on black, if black came up, but you lost $100, but now you got to pay $5 to play this game. Okay, so that means your winnings is going to be you either win 100 and then you pay $5 to play, so it's plus $95. Or you lose 100 and you had to pay $5 to play. You lose 105. And the probabilities are still the same. Okay. So remember the expected value or UX, or actually I should say, sorry, I should say expected value of X minus 5. Remember how we find the average? We take the value of each random variable times its probability and add them together. So it's 95 times 0.486 plus 95. And then plus negative 105 times its probability. And if you calculate that, you're going to get negative $7.80, which makes sense because remember when you didn't have to pay, the mean was negative 280. Now it's negative 780. It went down. You had to pay 5, so it went down by 5. Okay. So 5 less than the original mean. Of negative 280. So the mean will move with whatever you add or subtract. Okay. And we saw that or from unit 2, we saw that the standard deviation and therefore the variance wouldn't move. It would stay the same. And we could prove this. We could find the variance of x minus 5, which is the same as sigma squared x minus 5. And that's going to be 95 subtract negative 780 squared times its probability, 0.486, plus negative 105 minus the mean of negative 7.80 times its corresponding probability of 0.514. And the variance works out to, once again, 9,992.16, which means the standard deviation, if we take away 5, is going to be the same. And it was 99. Doesn't change. So we just proved this. Okay. But if we take all the numbers of the random variable can take on and multiply or divide by some constant, everything changes that same way. So if we times by 7, the mean we multiply by 7, the standard deviation we multiply by 7. Okay. If we divide by 3, the mean gets divided by 3, the standard deviation gets divided by 3. Okay. So we haven't really talked about the shape of a probability distribution yet, but it remains the same. Like if you were to sketch it out, if you were to draw it out on a graph, the center, which is the expected value, or mu, remember this is the same thing as EX, changes by that constant amount, whether we add or subtract. Variability doesn't change. So just to show you what happens when we multiply or divide, let's take the same situation, except now you don't have to pay for the game, but your winnings and losings get doubled. So therefore, the two random variables will be plus 200 or minus 200 and their corresponding probabilities. So if we find the new mean and new standard deviation, those should be doubled as well, right? So if we did this for mu2x, we take the new values, 200 times its corresponding probability, plus negative 200 times its corresponding probability. And when you do that, it's going to work out to, surprise, surprise, negative $5.60, which was twice the original mean. It's twice the original mean. -280. If we did the variance and then get the standard deviation from that, it should double. So it was 99.96. We should get 199.92. It should double. So the variance or sigma squared, sorry, this is 2x. We take each random variable value. So 200 minus the mean, -5.60 squared times its corresponding probability. Should know these numbers by now. And then add the other random variable value, -200 minus the mean squared times its corresponding probability, which works out to 39,968.64. But then the standard deviation would be the square root of works out to approximately 199.92, which was double the original standard deviation. Notice though, the variance is not doubled. Okay. The original variance was what? Almost 10,000. Yet this one is almost 4 times that much. That makes sense because if the standard deviation is twice as much, the variance should be twice as squared as much. Because variance is equal to standard deviation squared. So just to sum this up, if you were to graph this, it'd be a very simple graph, be the same. Center changes by whatever we multiplied or divide by, so the mean. Standard deviation changes by whatever we multiply or divide by. Okay. Last portion. What happens if we take 2 different situations and their random variables and combine them? Okay. So, as an example, people who play the casinos play more than just roulette. So say that you play the slots, which are the things that you hold. And you get 3 of a kind or 5 of a kind, you make lots of money. You put in $20. The slots are programmed so that you have a 20% chance of doubling your money and an 80% chance of losing your money. Here's the probability model here. So Y is going to be equal to the winnings from the slots. So 20% chance of winning, or sorry, of doubling your money, so plus 20. 80% chance of losing your money. What happens to the expected value or the mean and the standard deviation if we add the 2 games? So you're going to play both games. Okay. So remember, and here you've got all the information. So the mean of this game is -$12. That's not great. Okay. The variance is $256, and the standard deviation, which is the square root, is 16. Okay, so you're given all that. We don't have to calculate all that. And remember from roulette, So from roulette, the mean, and we called it X, was negative $2.80. The variance was, variance was $9,992.16, and then we square rooted that to find the standard deviation of 99.96. Okay, so this is what we have for the slots. This is what we have for the roulette. What do you think the mean would be if you played both? What do you think you'd do? Common sense. The mean of roulette, add them. Add them. That's all you have to do. So to find the mean of X and Y, we just have to take the mean of X plus the mean of Y. So in this case, it would be negative 2.80 for the roulette wheel, negative $12 for the slots, gives us negative 14.80. I didn't leave enough. I gotta change this. I didn't leave enough room. Yeah, I'm gonna sort of block this off. The standard deviations. Well, one would think that we would just add them, right? But no, we actually don't. And without going into all the calculations about it, which I used to do, but took a really long time, you can't add their standard deviations, but you can add their variances. Okay? So you can add the variance of X plus Y will equal the variance of X plus the variance of Y. So you can go that route to get the standard deviation. You'd have to square root it out, yes. So the variance of X, we had 9,992.16 plus the variance of Y, which is $256, gives us 10,248.16. And then to find the standard deviation of X plus Y, I just square root that 10,248.16. Okay, and I get approximately 101.23, $101.23. Notice that is not the sum of the standard deviations. That is not 99.96 plus 16. So when we combine two random variables, just to get the new mean, add the two means. To get the new standard deviation, add the variances and then square root. Okay. Finally, what if we subtracted the two variables? Okay, and we can't really use the casino games here as an example of that because it doesn't really make Like you go and play roulette and then you don't go and play slot, that doesn't make sense. So I'm just going to make up some numbers. So let's say we've got one situation where X was the random variable, the mean or expected value was 2, the variance, okay, was 4. And then there's another event with Y as a random variable, its mean was 3, and its variance was 25. Okay. How do you think you'd find the new mean? What's that? Don't overthink. Add. Remember, Z is equal to this minus this. Subtract. So, the mean of Z is going to equal the mean of X minus the mean of Y, which gives us 2 minus 3, which gives us -1. Okay? So what do? We subtract their means. Now this is really going to upset you. And again, the explanation is actually very long. One would think, with the standard deviation, that what you would do is you'd subtract their variances and then square root to find the new standard deviation, right? You actually add their variances again. Why do you add their variances? Short explanation. Remember, variance is spread. It's how spread out something is. So even though there's differences and some are negatives, the spread is still the same. So we actually add their variances. So to find the standard deviation of Z, first of all, I got to do the variance. And it's going to be the variance of X plus the variance of Y, and then square root that answer. So this is going to be, what's the variance of X? The variance of X is 4, plus the variance of Y is 25. So the variance of the difference of the two, I know it sounds weird, is 4 plus 25. Okay? And again, there's a very lengthy explanation for that. Why it stays as addition. But just for your purposes, just remember it as addition. Right? So then the new standard deviation of Z will be the square root of 29, which will give us approximately 5.39. Okay? So when you combine two random variables, when you add them, you add their means, add their variances, and square root to get the standard deviation. When you subtract two random variables, you subtract their means, but then you do the same thing with the variances that you did with adding. Add their variances, square root to find this new standard deviation. Okay? That's really all I want you to remember from this. Honestly, I think what they're doing, I don't know if they've done it yet. There was a survey put out last year. I think they're actually removing this.